Hey there, fellow scientists. Welcome to Galileo's AP STEM. Today we're covering topic 2.1 of the AP Chemistry curriculum, so if your mind is ready to synthesize, then let's learn the different types of chemical bonds. So what exactly are the different types of chemical bonds? These, my scientists, would be ionic, covalent, and metallic bonds. But before we can understand bonding, we have to look at the periodic table, because where an atom lives tells us exactly how it behaves. First, let's talk about the driving force of bonding, electronegativity. This is a measure of how badly an atom wants to hog shared electrons. As we move from left to right across the periodic table, electronegativity increases. Why? Because we are adding more protons to the nucleus, increasing the positive charge without adding new electron shields. In turn, this increases the pull on the electrons, decreasing the radius of the atom. Okay, so as electronegativity increases, the radius decreases. But how is this even important? It's important because of Coulomb's law. In the context of chemistry, Coulomb's law states that the electrostatic force between electrons in the nucleus, aka the protons, is directly proportional to the charge. Do you see these two Q's? These represent the charges of the two separate charged particles. And when we're talking about the electrostatic force, this means electrons and protons in a single atom. And just look at Coulomb's law. The radius is inside the denominator, meaning when the radius decreases, force increases because they have an inverse proportionality. Now we have talked about going from left to right across the periodic table, but what happens when we go down? Well, as we go down the periodic table, a very important thing happens. We add an electron shell. And if you have some insight, when we add a shell, the radius gets bigger. And as we know, according to Coulomb's law, as the radius increases, the electrostatic force decreases. And this is exactly why as we go down the periodic table, electronegativity of atoms decreases. And remember how electronegativity increases as we go from left to right? This leads to specific charge patterns. Elements on the left, group 1 and 2, have low electronegativity and low ionization energy, so they lose electrons easily to become positive 1 or positive 2. And contrastingly, elements on the right, like group 16 and 17, have high electronegativity, so they gain electrons to become negative 1 or negative 2. And this, my scientists, is exactly where ionic bonding comes in. To review, in ionic bonds, electrons are being given to one another, where the negative atom gives electrons to the positive atom that needs them. So when you look back at the periodic table, we can see that elements in group 1 and 2 can form ionic bonds with elements in group 16 and 17. For example, we all know about NaCl, the iconic, or should I say ionic bond. What are you looking at me like that for? That was funny. So now that you know that it was funny, back to what I was saying. This is because sodium, Na, is located on the left side of the periodic table in group 1, so it has a positive 1 charge. Chlorine, Cl, is located on the right side in group 17, so it has a negative 1 charge. This way, one electron is transferred from chlorine to sodium, forming the ionic bond. Oh yeah, and I forgot to mention, sodium is a metal and chlorine is a nonmetal. This is because in ionic bonding, you typically have a metal bonding with a nonmetal. However, there are exceptions to this, so do not take this to the bank with absolute certainty with every single metal and nonmetal that you see. But what if two nonmetals bond instead of a metal and a nonmetal? This is where covalent bonding comes in. Instead of giving or taking electrons from each other, they share them. However, not all sharing is caring. This is because there are two types of covalent bonds. The first type is nonpolar covalent, so electrons are equally shared. It is called nonpolar for a reason because there is an equal amount of electrons on both sides, so the charge remains the same. The second type is polar covalent. This happens when two nonmetals of different electronegativities bond together. Since one atom is more electronegative, it can attract more electrons to its side, creating polarity. And a perfect example of this is the one and only H2O. Oxygen is extremely electronegative compared to hydrogen. Just look at the periodic table. Oxygen is all the way on the right, while hydrogen is stuck on the left. Since oxygen is so electronegative, it attracts more electrons than hydrogen does, creating a charge imbalance where oxygen has more electrons in its side and hydrogen has less. And if you have more electrons near the oxygen side, that makes the oxygen slightly negative, while the hydrogen, with a lack of electrons, is slightly positive. And if you can smell it, that's a charge imbalance, which is exactly why a water molecule is slightly polar. We visualize this polarity using a little something called a dipole arrow. And two things that you need to know about the dipole arrow is that it points towards the atom that is the most electronegative. You also need to know that the dipole arrow will be longer if there is a greater difference in electronegativity between two atoms. And don't be confused, there can be more than one dipole arrow if there is multiple bonds. For example, there are two bonds in H2O, both of them being between oxygen and hydrogen. So there would be two dipole arrows pointing from hydrogen to oxygen since oxygen is more electronegative than both of the hydrogens. Now we move on to what we've all been waiting for, metallic bonds. In metallic bonding, a metal attaches to another metal, and one key thing about metals is that they have very low electronegativity. So when two metals bond, neither atom is very good at holding on to their electrons. So when these metals bond, the valence electrons detach from their specific parent atoms. We call these delocalized electrons. Delocalized electrons flow freely through the structure, creating what we call a sea of electrons. The metal atoms become positive cores floating in the sea of negative glue. And this, my scientists, is exactly why metals can conduct electricity, because their electrons are free to move and carry a charge. So let's put diagrams of all three chemical bonds side by side so you can really visualize the difference. In ionic bonds, we have a rigid lattice of alternating positive and negative ions. For covalent bonds, we have distinct molecules where atoms overlap and share electrons. And in metallic bonds, as we just covered, we have positive nuclei in a chaotic, flowing sea of electrons. Now, if you want to know about intramolecular forces and potential energy, then go ahead and subscribe and check out the next video. I'll see you in the next one.